5 seconds.
Okay, good. Thank
So
you.
it's up to you, Hamza.
Okay, great. Thanks a lot. Good morning, everyone. So thanks again for joining this third session on this short course on optimization for data science. So just to recap, so yesterday we first session we looked at some a quick preliminary of some very basic convex analysis and yes, so some very basic convex analysis and convex properties of convex functions. Recall the definition of a function being L smooth and a function being strongly convex. Remember, these were the key definitions that we saw. And in the second session, we analyzed the gradient method and we gave bounds on the convergence rate of the gradient method. So what I would like to do in this morning session is to analyze, try to explore something called fast gradient methods. So these are a class of methods that look very similar to the gradient method. So the iteration rules are just a small modification of the gradient method, and yet the convergence rate is usually is faster and sometimes even significantly faster. Okay. So these have been quite popular in the last maybe 10 to 20 years since they were discovered. Okay, so okay, just to recap here. So this is the gradient method that we saw yesterday. So I want to minimize. Okay, I didn't write the problem, but I want to minimize the function f of x, and my iterate xk plus 1 is xk minus tk times the gradient of f at xk. And tk is a step size. We discussed a bit how one can choose such a step size. We saw that if you know the parameters of your function f, like the smoothness constant or the strong convexity constant, then you can choose tk according to this knowledge. And if you do not know them, then you can do what we call a line search. And I explained the property, the concept of a backtracking line search at the end of the lecture yesterday. Okay, so what did we prove yesterday? So we proved two results on the convergence of this gradient method. One assuming that the function is strongly convex, and the other is assuming the function is simply L smooth and without any strong convexity assumption. Okay, so assuming that the function is strongly convex and L smooth, we saw that if you choose the step size according to this equation here, tk is 2 divided by m plus L. Then the distance to the optimal point, x star, decreases at a linear rate. Okay, and the rate of convergence is this c minus 1 divided by c plus 1. Okay, where c here is L divided by mu is called the condition number of the function. Okay, and this is bigger than 1. Okay, so obviously, I mean, when C is large, okay, maybe I should have written this yesterday. So when C is large, okay, so this C minus 1 divided by C plus 1, okay, so this is roughly just 1 minus 1 over C. Okay, this is just, it's useful to have this approximation in mind. Okay. So this is really 1 minus 1 over c to the power k. Okay, so when the function is just L smooth without assuming anything about strong convexity, what we saw is a much weaker convergence rate. Is sublinear convergence rate, and we saw that the function values approach the optimal value f star as a sequence like 1 over k. Okay, so it's less than L divided by 2k times the norm of x0 minus x star squared. Okay, so we saw that this is sublinear convergence rate. Okay, this is sublinear rate of convergence. Okay, and we saw that if you want to reach accuracy epsilon here, you need, in this case, we saw that you need roughly k to be L over epsilon iterations. okay, to reach a gap f minus f star to be epsilon. And here we saw if you want to reach a distance of epsilon, you will need roughly c log 1 over epsilon iterations. Okay, so both of these are, this is to reach accuracy epsilon. Okay, so obviously in both cases, I mean, here I'm talking about function values, the other I'm talking about distance to optimal point, but they're roughly the same. So it's okay. I mean, at least for the strongly convex case, you can convert the bound on the distance to optimum to a bound on the function values. Okay, so and I argued last time that C log 1 over epsilon is a much better rate compared to L over epsilon. Okay. Yes. So okay, and we illustrated this on some simple examples. I mean, I showed you the plot of what happens if you apply the gradient method to a simple least squares problem, and we observed indeed this linear rate. And we did the same for the other one on a logistic regression problem, and we did observe this this sublinear rate of convergence. So okay, so today, as I mentioned, what I want to talk about are these fast gradient methods. Okay, so what we will see is that if you modify the iteration rule of the iteration rule of the gradient method, so if you kind of change this, but a very simple change to it, you can actually gain quite a lot. Okay, so we'll see that you can change, you'll be able to change this c log 1 over epsilon to a square root of c log 1 over epsilon. Okay, which can be quite significant for problems. Okay, because c can be quite large. I mean, if think of if c is in the order of 1,000 or 10,000, then you can see that having a square root here can help you a lot in the number of iterations. Okay, and if your function is not strongly convex, okay, then also what we'll be able to get is a square root of epsilon. Okay, so this is what you can get by changing, slightly changing the definition or the iteration rule of the gradient method, and this is what we call the fast gradient method. Okay, so what I would like to do today is to explore how these fast gradient methods are defined. Okay, and we'll see a little bit of their convergence analysis, how we analyze their convergence. Okay. So this is exactly, this is what I was talking about. So by a simple modification of the gradient iteration rule, you can get an improvement over the convergence rate of the gradient method. Okay, so what is the, let's kind of, to motivate a bit the discussion, let's go back to a figure that we saw yesterday. And this is the gradient method applied to a simple quadratic function, okay, which is this scaled quadratic function, 1/2 of x1 squared plus gamma x2 squared, where gamma is bigger than 1. So in this case, actually, c is equal to gamma over 1. So it's just equal to gamma, this condition number. Okay, and what we observed is this zigzag behavior of the gradient method. Okay, so it moves along a certain direction, and then it moves along a different direction that is almost orthogonal to it, and so on and so forth, until it reaches the optimum. So what we would like to do, I mean, kind of a natural thing to explore is to try to make the gradient method not so local, but to try to have the gradient method remember a bit what the previous iterates were. Okay, so so this corresponds to what we call adding momentum. Okay, so we want to make sure that the direction is a very local thing, but also depends on what the gradients of the previous iterates were. So this is the concept of damping. So this is what I propose, and this is what people have proposed really, to try to stabilize, if you want, these oscillations of the gradient method. Okay, so now xk plus 1 is xk minus tk gradient of f at xk. That's the usual gradient method. But then now what you do is that you add what we call this momentum term. Okay, so this is plus a certain coefficient beta k times the direction that you took in the previous iteration. Okay, plus beta k times xk minus 1. Okay, so we can just a very simple, and we can see what happens on this example I showed on the previous slide. So on the left, what you can see here is the same picture with beta is equal to 0, so no momentum or no damping. And on the right, what you can see is the gradient method with a momentum term, and the beta I chose here is just 0.1. And so what you can see here is that the iterates are indeed damped. And so here we have, in this case, we have oscillations are reduced. Okay, so we have reduced oscillations. So having a certain beta strictly positive, this allowed us to kind of stabilize the gradient method and not having it oscillate and wiggle a lot before reaching the optimum. Okay, it's a very simple idea. I invite you to have a look at this web page. Okay, so it's an interactive demo of the momentum method, and it allows you to change the value of beta and to observe what the trajectory of the method will be in reaching the optimal point. It's also actually a very lengthy article about the momentum and exploring some of its properties and so on. So you can have a read. Yes, you can read this article if you want. Okay, so this is kind of the main idea of the momentum of the momentum idea. And indeed, what you can show, I mean, this iteration rule is sometimes also called the heavy ball method. Okay, so this is called sometimes. And heavy ball here is to indicate the idea that you're adding some momentum. Okay, that you have a heavy ball that you're carrying with you that induces some momentum in the way that you change, that you cannot change direction completely. You cannot change direction kind of suddenly, going from xk to xk plus 1. And this is usually due, I mean, this method is due to Polyak, also just to give some credit. So it's an old method. Okay, so we can, probably the simplest function that one would like to look at when you devise a new optimization method for smooth problems, the simplest function that you want to look at is a quadratic function. Okay, so we can try to see what is the behavior of this heavy ball method or this momentum method on a quadratic function. So I'm assuming here that, so this is the quadratic function I look at, and so the Hessian of f is just equal to a here. Okay, it's a constant. And so the strong convexity constant is just the smallest eigenvalue of a, and the Lipschitz, the smoothness constant is the largest eigenvalue of a. Okay, so the condition number is just the ratio of lambda max by lambda min. That's actually the condition number of A, of the matrix A. And so you can prove that the heavy ball method will have a faster convergence compared to the gradient method, and will have the convergence I mentioned in the first slide. That is, it will have, instead of having c minus 1 divided by c plus 1 to the power k, it will have square root of c minus 1 divided by square root of c plus 1 to the power k. Okay, so this means if you do, if you require that, if you assume that c is bigger, much bigger than 1, and that what you want is square root of c minus 1 divided by square root of c plus 1 to the k is equal to epsilon, okay, this will tell you that k is roughly square root of c log 1 over epsilon. Okay, log 1 over epsilon. Okay, which is what I mentioned last time. And this is, as I mentioned, this can be much smaller than c log 1 over epsilon. Okay, when c is big, and when c, as I said, is in the range of 1,000, 10,000, and so on, which is not, can be quite typical in applications to have such a condition number. Okay, so also, since some people asked me in the chat yesterday, in fact, this is for those of you who know what the conjugate gradient method is. So this is a method that is originally and mostly used for the solution of linear systems where A is positive definite, so which equivalently corresponds to minimizing a convex quadratic. So this rate achieved by the heavy ball method is the same rate achieved by the conjugate gradient method. So the conjugate gradient method also has the square root of c minus 1 divided by square root of c plus 1 to the power k. In fact, I would say that the conjugate gradient method is the method of choice to use for such problems. You should use it instead of using the heavy ball method. In fact, the conjugate gradient method it can be seen as a momentum method, but with a very specific choice of tk and beta k that I will not talk about in this lecture, because the conjugate gradient method is kind of not it's kind of a non-obvious method that requires a bit of development and so on. So I will not cover it in this lecture. But yeah, one should keep in mind that the rate achieved by the conjugate gradient method is this rate with the square root of c minus 1 divided by square root of c plus 1 rate. Okay, so what I would like to do now is to give you an idea of the proof of how do we prove such a convergence rate for the heavy ball method. Okay, and we will see in passing also what is the choice of t, the step size that you have to choose, as well as the beta, the damping parameter, in order to reach such a convergence rate. Okay, maybe before I do so, actually, let me just show you that this is not just in the math and the bound, but this is actually real. I mean, if I apply the heavy ball method on this convex quadratic, so on this least squares problem, 1/2 of norm of ax minus b squared, and I plot the error, then in blue is the gradient method, okay, which I showed last time. So this is the gradient method, the plain gradient method, and this is the heavy ball method. Okay, we see that both do have a linear convergence rate, but we see that the rate, the slope of this line, okay, is better in the case of the heavy ball method. Okay, it decreases faster compared to the gradient method. Okay, so the heavy ball method is as I said, I will analyze it for the case of convex quadratics. This is where the analysis is easy. In fact, the analysis for general F is more complicated. In fact, it's not exactly known when does it converge and when it does not. Okay, so it's not really the method of choice that people use in practice, but it's a good method to illustrate. I mean, in the context of teaching this fast gradient method, it's because it has a simple intuitive derivation, and the proof is also not very complicated. But the method of choice that one should use, for example, to solve this least squares problem, if you want to use an iterative method that converges fast, you should use the conjugate gradient method. This is really what you should use. Okay, so let me now go to the proof. Okay, so we'll prove that the heavy ball method converges at this rate of square root of the condition number minus 1 divided by the square root of the condition number plus 1. Okay, so let's so as you will see, for those of you who have some background in analysis of dynamical systems and so on, this is exactly what we will do. So we will write really what an algorithm is. You can think of it as a discrete time dynamical system. So you have a state xk, and xk plus 1 is a function of xk and on xk minus 1, and we want to analyze how fast this dynamical system converges to its equilibrium point, which is the solution of the optimization problem. Okay, so and so we will use techniques that are typically used in dynamical systems. So my function that I want to minimize, remember, is 1/2 of x transpose ax minus b transpose x. Okay, so the gradient of f is just ax minus b. Okay, and I know, and then, so this means that x star is just A inverse b. Okay, this is the optimal point that I'm trying to look for. So really minimizing, as I mentioned before, minimizing a convex quadratic is equivalent to solving a linear system, to computing A inverse b, to solving Ax is equal to b. Okay, so so now my iteration rule is xk plus 1, I mentioned, is so that's xk minus, so tk times the gradient, so in this case it's axk minus b, plus beta k times xk minus xk minus 1. Okay. So by the way, I'm going to assume here that my step size is constant, so t is equal to tk and beta is equal to beta k. So I'm just going to actually do this right away. So I'm going to erase, I'm going to have this t, and here I'm going to have just a beta. Okay. So this is really my iteration rule. Okay, and I'm going to collect together the xk and the xk minus 1. So I can rewrite this as, so I have 1 plus beta identity minus t times a xk. Okay, and then I have a minus beta xk minus 1, and then I have a plus b times t. This is a, or let me write t times b instead. So plus t times b. Okay. So this is really my iteration rule. So I have xk plus 1 as a function of xk minus 1, and then I have this constant term t times b. Okay, what I'm interested in is really xk plus 1 minus x star. Okay, so I can write xk plus 1 minus x star as this whole guy. Okay, so let me rewrite it. So that's 1 plus beta identity minus t times a xk minus beta xk minus 1 plus t times b minus x star. Okay. And now we do something that is usual, because x star is actually a fixed point of the equation. So if you want, it's the equilibrium of my dynamical system. I'm actually, what you can show, and this is a simple calculation, that this is equal to 1 plus beta identity minus TA, okay, times xk minus x star minus beta times xk minus 1 minus x star. Okay, so I can take this term here, okay, this constant term that I have here. I went into the contribution in here and in here. Okay, and you can very easily, using the fact that that x star is A inverse B, okay, you can show that this is indeed that this is an equality. Okay, that you can distribute that TB minus x star is equal to that essentially these two last lines are equal to each other. Okay. Okay, so yes, okay, so now let's do what I mentioned before. So let's write this down as we do when we study differential equations, or when we study dynamical systems. So remember, yeah, when we study such dynamical systems, when we have a system that is of second order, so this means that xk not only depends on xk minus 1, but also on xk minus 2, so on the previous iterates, a typical trick that we do is to augment the state space, so that the system that we're studying is of first order. The same thing we do with differential equation. If you have a differential equation of order 2, so this means that you have the second derivative of y is let's say a linear combination of y dot and of the first derivative of y and of y. Then we rewrite this as a differential equation of first order, but in a larger vector, in a vector that is y and y dot. So the y and its derivative. So that's exactly what I'm going to do here. Okay, so I can rewrite this recurrence relation, okay, as follows. So I'm going to write this as xk plus 1 minus x star, and xk minus x star as a certain matrix. Okay, so this matrix is going to be as a certain matrix times xk minus x star and xk minus 1 minus x star. Okay, so what I have here, I can just fill in then the this matrix. So I get 1 plus beta identity minus t times a. Okay, and then I have a minus beta identity here. And obviously the second line, this is always the same. Again, the trick that I mentioned, I will have an identity because xk minus x star is just xk minus x star. And then I will have a 0 here. Okay, so okay, let me write this down. So this is the usual trick in converting a second order differential equation or a dynamical system into a first order one. Okay, by augmenting the state space, by adding, in the case of differential equations, you add the derivatives in the state. Okay, so let me rewrite this dynamical system just here. So I can, what we have then is xk plus 1 minus x star and xk minus x star is equal to a certain matrix M times xk minus x star and xk minus 1 minus x star. Okay, where M is the matrix 1 plus beta identity minus t times 1 plus minus t times a, and then I have here minus beta identity, and I have identity and 0. Okay. So again, for those of you who have studied dynamical systems, we know what we have to do to study stability of a dynamical system. You know what you have to do is that you have to look at the eigenvalues essentially of the matrix. You have to look at its spectral radius. Okay. So so let's do this. But before I do so, let me just iterate this equation. So this tells me that xk plus 1 minus x star and xk minus x star, this is really m to the k times x1 minus x star and x0 minus x star. Okay. So this implies then that the norm of xk plus 1 minus x star and xk minus x star is less than the norm of m to the k times the norm of x1 minus x star and x0 minus x star. Okay, and here the norm, where the norm of m to the k is what I call the operator norm. So, okay, where the norm of m to the k, this is the supremum. Remember, norm of x2 is equal to 1 of the norm of m to the k times x. Okay, this is what we call the operator norm. Okay, and so we know, as I mentioned in dynamical systems, that when you raise matrix m to the power k and you look at a norm, this gets very close to the spectral radius of m raised to the power k. So I'm going to use here this result of convex in matrix analysis. If you come from a dynamical systems background, then this is something that you probably have heard about. So from matrix analysis or or dynamical systems, we know that the norm of m to the k is roughly equal, so I'm not going to be very precise here, but it's roughly equal rho of m to the k. Okay, so where rho of m, okay, is the max is the largest eigenvalue of M in absolute in magnitude. So lambda I eigenvalue. Okay, so okay, so now this this reduces then the question to studying really the eigenvalues of M. Okay, so we need to study. Okay, so we need to study. So we have to study eigenvalues of M. Okay, so let's remember what M looks like. So M is 1 plus beta identity minus T times A minus beta identity and 0. Okay, so I'm going to make a simplifying assumption here, which is actually without loss of generality. I'm going to assume here that A is diagonal, just to make the analysis simpler. But in fact, this is this is without loss of generality, because you can actually diagonalize A, because A here is symmetric, so you can diagonalize it in an orthogonal basis. And so it is very easy to see. A simple argument allows you to see that by just kind of doing a change of basis, you can put so you can put A into a diagonal matrix, and that won't change the eigenvalues of M. So okay, so I'm assuming that A is diagonal. So assumption, so simplifying assumption, if you want. Let me just write assumption. Assumption A is diagonal. So A is diagonal. So okay, so now let's, if we assume that A is a diagonal matrix, we can have a look at what this matrix is going to look like. Okay, so this matrix is defined by block. Okay, so the identity matrix is obviously a diagonal matrix. So I subtract A plus beta identity minus TA. So I have a diagonal matrix on the first block here. Okay, so I have a diagonal matrix, and this is minus beta identity, and 0. Okay, so I really have these, each block here is a diagonal matrix except the bottom right block, which is a 0 matrix. Okay, so now to analyze this matrix, I mean, if you do a bit of matrix analysis and so on, then it's not very difficult then to see how you would like to proceed in analyzing this matrix. So really, what you can see is that if I permute the rows and the columns of this matrix, I can put this matrix into a block diagonal form with 2 by 2 blocks. Okay, so so by permuting, so rows and columns of M, so you can show that M, okay, so is similar to, so up to permuting the columns is a block diagonal matrix, so M1, M2 up to Mn, okay, where each Mi is 2 by 2 of the form Mi is just now 1 plus beta minus T AII minus beta 1 and 0. Okay, so it is a 2 by 2 matrix that only depends on the II entry of A. Okay, and so you can see that to analyze the eigenvalues of M, I just need to analyze the eigenvalues of a 2 by 2 matrix, which is a simple task. Okay, so now only need to analyze eigenvalues of a 2 by 2 matrix. Okay, or this bunch of 2 by 2 matrices, but they're all of the same form. So you just have to do it, the analysis for one. Okay, So okay, so I need a bit more space here. So okay, so I'm not going to do this this calculation in detail. I'm just going to tell you what the result is, so that it doesn't take too much time here. So what you can show is that if you choose, let's see, so if you choose the following two constants, so if you choose t to be equal to 4 divided by square root of m plus square root of l, okay, and if you choose beta to be equal to, so square root of c minus 1 divided by square root of c plus 1 squared. Okay, if you make this choice of t and beta, you can prove that all the eigenvalues of m, okay, so you really just have to prove it for each mi, because the eigenvalues of m is just the collection of eigenvalues of the different mi's, are less than, so have magnitude, sorry, so have a magnitude, at most square root of c minus 1 divided by square root of c plus 1. Okay, and so this is exactly what we wanted. So this tells us then that that the norm of xk minus x star is at most this square root of c minus 1 divided by square root of c plus 1 raised to the power k times the norm of x0 minus x star. Okay, so this proves essentially now that this essentially finishes the proof. So this essentially completes the proof. So if you put everything together, okay. Okay, so just what you want to remember is that the idea of really looking at an optimization algorithm as a dynamical system, as a discrete time dynamical system, and using relatively standard tools from the analysis of dynamical systems and some matrix analysis to analyze this algorithm. Okay, so maybe I can actually write this. So key idea of the proof is to interpret optimization algorithm as a dynamical system and use standard tools from this area, from matrix analysis, to analyze its convergence. Okay. This has actually been quite, I mean, recently this approach of using tools from dynamical system to analyze optimization algorithm has been quite a fruitful approach in the recent years. Okay, so now so let's okay, so maybe what I would like to do now is, as I mentioned, I mean, the heavy ball method. Can we mute the participant here? Okay, thanks. So yeah, so I mentioned that the heavy ball method, we did the convergence for convex quadratics, so for x transpose ax minus b transpose x. What about for general nonlinear non-quadratic functions? Okay, as I mentioned before, that the convergence analysis of this method is not is not yet well understood. I mean, it's still actually an area of research. Okay, but there is actually another method that looks very similar to this heavy ball method, but it's just slightly more complicated. That has been shown by Nesterov to achieve this optimal rate of convergence. I mean, this improved rate of convergence for the whole class of functions that we're interested in. So for all strongly convex functions, and there is also a fast the fast convergence rate for all L-smooth functions. Okay, and so this is how this variant of the heavy ball method looks like, or the gradient method looks like. That is due to Nesterov. The only difference with the heavy ball method is that the gradient is not taken at xk, but rather is taken at a certain extrapolation of xk. Okay, so so let me here draw a simple picture. So really, what's happening in this method of Nesterov is you have, so let's say that you have xk minus 1. This is your iterate at k minus 1. This is your iterate xk. So what you do is that you first extrapolate. So you extrapolate xk to a certain point y, okay, which is xk plus beta times xk minus xk minus 1, okay? And then what you do is then you do a gradient starting from y. So you take a gradient step from y, okay? So you look at the gradient at y, so this will be minus the gradient of f at y, and this is going to be your new iterate xk plus 1. Maybe I should have used some colors, okay? But this is okay. This is really what happens, okay? So if you let y to be xk plus beta k, xk minus 1, this is a way of rewriting the algorithm. So what is in here? It's exactly the same algorithm. So you see that you first compute this extrapolation, and then you do a gradient step from this extrapolated point. Okay, this is an algorithm that Nesterov has proposed, that he invented essentially. And what he did, I mean, the main result is that this method has the desired rate of convergence. I mean, let's see. Yes, so it has the desired rate of convergence. So this means that if f is m strongly convex and L smooth, okay, then the distance from optimum is at most square root of c minus 1 divided by square root of c plus 1 to the power k. So we have the square root of c again, where c is the condition number. And if f is L smooth, and this I only mentioned at the very beginning, if f is L smooth, then the function value f of xk minus f star is at most 1 over k plus 1 squared. Okay, so times the norm of x0 minus x star squared and times n. Okay, so again, we see here the comparison with the gradient method is that you have the square root of c involved in the rate in the strongly convex case, and in the non-strongly convex case, you have a 1 over k squared instead of 1 over k. So yes, so this means again in here that if you want to reach accuracy, if you want f of xk minus f star epsilon, then this would mean that you need this means that you need roughly k L divided by square root of epsilon iterations. Okay, and here, as I mentioned before, if you want norm of xk minus x star to be epsilon, you will need square root of c log 1 over epsilon iterations. Okay, and what is important here is that this works for any function f. I mean, it doesn't have to be quadratic. So, okay, and so as you can see, this method is also very simple to implement. So I've implemented it here for a problem in logistic regression, and so what you see here. So again, I should have written this. So this is the gradient method. Okay, and this is the fast gradient method of Nesterov. Okay, so we see that there is really a significant improvement compared to the gradient method. Okay, so as I mentioned, for this reason, because it's just really, it doesn't cost you much, and you get a much better convergence rate. For this reason, these methods have been quite popular recently for various applications, for problems in statistics, but also for problems in imaging and so on. So in inverse problems. And so on. Okay, so yes, so I will not actually do the proof of this theorem because it's of this convergence rate, because it's actually not at all trivial. It's quite a difficult proof, and so I will not explain. I will not do it here. That's the reason I try to do this heavy ball method, because it's comparatively much simpler. And at least we have some intuition of what is happening in here. Analyzing the Nesterov's method is quite, there are certain steps that are not very intuitive. So, but maybe I'll just mention one thing is that, again, there is something, the key ideas that we use, again, are coming from dynamical systems. And the key lemma is to show that a certain quantity decreases with the iterations. And so in terms of, in a dynamical systems, parlance, this is called a Yapunov function. So essentially what you show is that you exhibit a certain Yapunov function. In this case, this Yapunov function is something, okay, that Nesterov came up with, and it's a certain combination of the distance from optimum in function value, so f of xk minus f star, and a certain distance to optimum, so the square distance to optimum, so norm of vk minus x star. So here I did not really explain what vk and theta k are, but these are auxiliary sequences that you define when analyzing the algorithm, which I did not define. But roughly, maybe if there's one thing you want to remember, it's the analysis involves having a clever Lyapunov function that you show decreases along the trajectory, and then this allows you to prove the desired convergence rate. So maybe one important point that I should mention about this method is that this method is not a descent method. So unlike the gradient method, we saw that f of xk plus 1 is always strictly less than f of xk. For the Nesterov's method, this is not the case. It is possible that iterate xk plus 1 has a higher function value compared to the previous iterate. Okay, but obviously, in globally, the thing will decrease and will go to f star. Okay, so I think that's all I wanted to say about Nesterov's method. So let me just kind of conclude this discussion of fast methods by asking, okay, so we've started with the gradient method. We've shown that one can improve them and get a better rate. Can we further improve on these accelerated methods? Can we get a better convergence rate? Okay, for example, instead of having a dependence on 1 over k squared, like at iterate k, you get 1 over k squared. Can we get something like 1 over k cubed or 1 over k to the 4? Okay, so this is a question that one can ask and one can formalize, and the answer actually turns out to be no. So in a certain sense, this method of Nesterov that I just showed is optimal. Okay, in that in a certain sense, you cannot improve over it. There is no algorithm that can achieve a better convergence rate. Obviously, I said I'm saying in a certain sense because it depends on how you actually formalize the problem of how you actually formalize the problem, and I will show one way this problem has been formalized and one way it has been, and why the answer is in a certain sense no. Okay, so how do we formalize this question of can we improve on these accelerated methods? The way you do this is that you consider a class of algorithms and a class of functions, okay? And you try to see for a certain algorithm, what is the worst possible function that this algorithm will perform on, okay? And you try to see what is this, what is the solution of this min-max problem, okay? So it's kind of a game, so I'll try to, let me explain it. So, so we consider the class of algorithms that we consider is a very general class of algorithms where you're allowed to query at each step you're allowed to query the gradient of the function that you're trying to minimize at a certain point xk. Okay, and the next step is then going to be a linear combination of all the gradients that you have queried so far. Okay, so you start from a certain x0. We assume that this is fixed, so x0 is fixed. You query the gradient of the function at x0, so this will give you a gradient of f at x0. So x1 is going to be a linear combination of x0 and the gradient of f at x0. And then you query the gradient of f at x1, you'll get a new vector, and then your new iterate is going to be a linear combination of all these, and so on and so forth. Okay, so this is a class of algorithm, of course, depending on how what is the linear combination that you do, this will tell you what the algorithm is. So obviously it's easy to see that the gradient method and the fast gradient method and the heavy ball method all belong to this class of algorithms. Okay, so we consider all possible algorithms that look like this, and we want to understand what is, for a certain given algorithm, what is the worst possible performance of such an algorithm on a function. Okay, so obviously one has to first, to scale things correctly, one has to define a class of functions on which I'm going to let your algorithm run on. Okay, and in this case, I'm going to look at L-smooth functions. Okay, so functions for which the second derivative, the Hessian, is at most n. Okay, and so the result tells you that, and this again was proved by Nesterov. So I'm going to fix L, so this is the L smoothness of my function, and an integer k, and then the claim is that for any algorithm, so you choose an algorithm, you design the algorithm that you like, and so from this algorithm that you design, I'm going to give you a certain function f that is convex and that is L smooth, and I guarantee to you that after k steps of your algorithm, the function value f of xk minus f star is going to be at least something like 1 over k squared. Okay, so so let's make sure that we interpret this this theorem in the right way. So you should really think of this theorem as a game played between two people. So someone coming up with an algorithm and the other person coming up with a bad function on which the algorithm will perform badly. Okay, so what this result is telling you is that for any algorithm that you design, there's always going to be a bad function on which this algorithm will have a convergence rate that is at least, I mean, that is worse than 1 over k squared. Let me say worse instead. Okay, so I hope kind of that is the statement of this theorem is clear. So maybe, I mean, one caveat about this theorem that I'm going to that one has to be aware of is that the function that is going to be constructed is quite a high dimensional function. Okay, that in fact the dimensionality, this xk, the dimension of this xk will happen to depend on k. So in that sense, this theorem can be unsatisfactory in a certain setting if you have a certain prior information about what the dimension of x is. Then this theorem does not apply anymore. Okay, so so maybe let me briefly mention what is involved in the proof of such a result, even though this is not an algorithm, this is just a kind of impossibility result. But let me briefly, just so kind of you get an idea. The function f, this bad function f, is actually a very simple function. It's just a quadratic function. And it is given by this formula. So this is, again, this formula, you can read it off in Nesterov's result in his proof. Okay, so it is a quadratic function that has been designed to have a kind of a special property, which is the following. So first I define certain subspaces. So I define Vi just to be the subspace spanned by the first I coordinate vector, so x1 up to xi. Okay, and the main property of this function is that if you take a point x in this subspace, then the gradient lives in the next subspace in Vi plus 1. Okay, so you can at most So what this actually tells you is that if you are at iterate, if you have an iterate that lives in a certain VI, then the next iterate can has to live in at most can only live in VI plus 1. Okay, and so what this means, if I start from x0 is equal to 0, then this means that the kth iterate of the algorithm has to live in the subspace Vk. So it means that only its first k components can be non-zero. Okay, so this tells us also that the value obtained at the kth step of the algorithm cannot be better than the minimum of this function f on this subspace, if you just restrict the minimization to be on this subspace. Okay, and so the kind of the proof is finished. What you just have to do is to compare the minimum of f on this subspace Vk with the global minimum of f. Okay, so this is really the steps of the proof. I will not kind of do the details because it's not very important. But I think it is, I mean, this is a very popular, I mean, it's in the area of convex optimization, especially first order optimization and so on. This is a very well-known result about the limitations of first order methods, essentially that you cannot, in general, if you're interested in optimizing very high dimensional functions, there is no optimization method that only depends on the gradient that can achieve a convergence rate better than 1 over k squared after k iterations. There is a similar result you can show about if your function is strongly convex, to show that this square root 1 minus 1 over square root of c rate is the best that you can achieve. Okay, so maybe I'm going to, let me just, I mean, now this is kind of everything I wanted to say for this morning session. I finished a bit early here. So really, the key punchline that you should remember is that I mean, by doing a simple modification to the gradient method, one can get improved rates, and in some cases significantly improved rates. You go from the c log 1 over epsilon iterations to square root of c log 1 over epsilon, where c is the condition number, or you go from 1 over k to 1 over k squared in the case of just L smoothness and without strong convexity. Okay, so I mean, these methods have been implemented. These ideas based on momentum are quite useful in practice. So again, this is something that is not just of theoretical interest, but is of significant practical interest as well. Okay, so I will stop here, and maybe let me see if there are some questions. So let's see. How do I see this? Okay. Okay, so I do not see any questions. Let's wait a bit. And so some people have asked me about the slides. So I will try today to put the slides online, to set up a web page and put the slides online and give you the link to the slides. I will try to do it hopefully this evening, so after this afternoon session.
Okay, thank you, Professor Pr.Fawzi. Are there any questions?
Someone is saying, can you simulate this algorithm in Matlab? Yes, in fact, I did simulate it. So let's see. Okay, let's see. My iPad is a bit. Yes, so I did actually show you a plot where I implemented this fast gradient method and the heavy ball method. And I've shown you that compared to the gradient method, it gives a significant improvement. Yes. Mm-hmm.
Any other questions?
Okay, any further explanation on the impact of problem dimension? Okay, so yes, so maybe one thing that I actually did not, that maybe I should have, yes, indeed stressed, is that all the convergence rates I gave, like the square root of, I mean, the one, if you assume your function is strongly convex, I mean, the square root of c minus 1 divided by square root of c plus 1 to the power k, or the 1 over k squared, the dimension of the problem does not show up at all. I mean, there is no n. I mean, if my x lives in Rn, as you can see, all my expressions do not involve any n. So this is something that we call dimensionless convergence rates. So a priori, these rates apply to functions on very high dimensions, even of infinite dimensions. Okay, so there is no n involved. Obviously, the n is going to be hidden a little bit in, for example, in the norm squared. Okay, so you have a norm squared, norm of x0 minus x star squared. Okay, this will be impacted by the dimension. Okay, and another aspect where n is going to appear, obviously, and this is something that one cannot avoid, when you implement this algorithm, the cost of each iterate, you have to add up vectors. I mean, in the case of the gradient, you add up vectors in Rn. So the cost of adding vectors in Rn is linear, so it's of size n. And then then there's the cost of computing the gradient. The cost of computing the gradient can depend on how the gradient is given, but in the case of a convex quadratic, the gradient is a matrix vector multiplication, right? So it's a times x. And so a times x costs you in general n squared. So this is where the dimension of the problem will appear in the computational cost of implementing the algorithm. But in the convergence rate, as I mentioned, the convergence rate are what we call dimensionless. They do not depend on the dimension. In other, let's see, so there is kind of other literature in optimization where we analyze optimization algorithms in finite dimension. So where we're looking for bounds, rates, when that depend on the dimension of the problem. But these I will not talk about except maybe in the very last session. Okay, when I talk about path following interior point methods, we will briefly touch on dimension. Okay, so yes, but that's a good point. Yeah.
Are there other questions? Okay. So
someone is asking about some interesting books. Yeah, so there are many books in there are many books on optimization and on this concept. So I mean, there is a book by Nesterov. I mean, there are many books. I'll try to maybe compile a list, and maybe when I set up this webpage, I'll try to put some links to some books. Yes, I will try to do this today, and I will put it on the webpage. But essentially, there is a book by Nesterov, where he covers a lot of what I'm doing here. There are some online lecture notes that are also very good, some slides and so on that I actually I took a lot of inspiration from, so like the slides of Liev and Vandenberg at UCLA, or the slides of Stephen Boyd at Stanford. And yeah, so I'm going to put some links. Actually, maybe I can put some links right now, and I can put more on the web page if you want. So so this is a very these are slides. Let's see. By Professor Vandenberg from UCLA. Okay, that covers some of the things that we've seen here. In fact, this webpage that I've just put here itself has a list of books that you can have a look at. Okay, so these are actually good. Yeah, so this should give you a good reference on these topics. Okay, so if there are no more questions, I guess we can maybe stop here and resume in a couple of hours. So what I would like this afternoon, what I would like to talk about are non-smooth optimization problems. Okay.
Okay. If there are no more questions, thank you so much, Hamza.
Yeah, no problem.
And okay, we meet all again at a few minutes before 2 o'clock.
Okay. Yes. Okay. Thank you.
Thank you.
No,
bye to all.
Bye-bye.
Bye-bye.
Bye-bye.